Hello, everybody on Zoom. Okay, you can just start with attendance. Y'all can go ahead and sign in with attendance. And get your eye clickers ready. And please, y'all, put your masks on while we are in here together. Okay. So I was a really bad mom yesterday, and I forgot to put a joke in my son's lunchbox. I know, it was terrible, but I did remember today. So y'all want to know today's? It's a really classic third grade joke. What is big, gray, and goes round and round? An elephant on a carousel. You know, every so often, or, you know, periodically, I make bad jokes. And I'm the only one who laughs at my own jokes. It's okay. I'm good with that. Because of my periodic scarf, right? Periodically. All right, so it's just a bad joke day, but that's okay. It's fun. All right, last class period told me I have been messing up on Moodle. So I'm going to go home and fix it tonight. But I have been posting your exams as worth 120 points. Your exams are worth 100 points. My other class, they're worth 120 points. And I was putting yours as 100 points. So if you go in the syllabus, you will see that they are worth 100 points. So I'm going to go in and fix those tonight. And so you'll see your upgraded grades tomorrow. But it's not going to make too much difference in your grade. It's still the same grade. It's just worth a different percent of your total score. If that makes sense. Okay. So, but if you go in here, you'll see, okay, you'll see, right, they're worth 100 points each, right? So I'll go in and fix that. Okay. What else? Everybody did attendance. Go ahead and do attendance if you have not done attendance. I'm gonna close that. Okay, so since we had an exam last class, I thought that we could do some clicker questions from that section of chapter 5 that we did last Tuesday, a week ago. I had to count the days in my brain. So it's been a week, but I thought it would be a nice refresher for our clicker questions to do that. So they should be a review of what you watched in lecture and what we did in class last Tuesday. So this is a good chance for you to get some of those points. All right, let me minimize this. It's like everything's got to be just right for this to work. All right, so I want to stop this one. All right. So in an energy diagram, and I'm going to give y'all a minute and a half. So in an energy diagram for a reaction, you have to remember what an energy diagram is. The products are shown at a higher level than the reactants. What must be true? What must be true about this reaction? A little bit better. Give 20 seconds. And if you have not clicked in, click in. It's supposed to be a minute and a half. All right, so what you had to remember is what is an energy diagram? So what is an energy diagram? Right? We have energy here, and then we have what at the bottom? Time or progression of our reaction, right? So we're always going to go from reactants here to products here, right? So we have an energy diagram per reaction where the products are shown at a higher level. So products are up here and reactants are down here. What must be true about this reaction? How about A? The reaction absorbs energy to form the products. True or false? This one's true. This one's true. Super easy, right? This is low energy, lower energy. This is higher energy. How do you go from low energy to high energy? You absorb energy, right? Okay, it's exothermic. Nope, nope. Delta H is less than 0. Delta H is what? What does delta H represent? Enthalpy, right? Remember entropy and enthalpy. Enthalpy is heat. So that's not true, right? That would be an exothermic reaction. The potential energy has decreased. Remember you're on the bike, right? If you're on the bike, do you want to be a reactant or do you want to be a product? I want to be the product at the top of the hill, right? So really, if I'm sitting, if this is me, look at me. I'm so happy to be, no, I'm not happy to be at the bottom of the hill because that means what? I have to pedal. I have to put a lot of kinetic energy in to reach the top, right? So my potential energy has increased, okay? All right, and the last one, the products are more stable than the reactants. The higher your energy, the less stable you are. So that is not true. There's actually the opposite, or you could say less, right? Okay, so what do we say? Okay. All right. And this is just a pretty picture, right, of the same picture I drew, but just a little bit nicer. Ooh, wrong way. All right, so now you have a pretty energy diagram here. I want you to select the correct statement regarding the reactions represented by the energy diagrams. Thank you, Trinity. So select the correct statement regarding the reactions represented by the energy diagrams. I'll give you a minute and a half. And remember, for these clicker questions, anything that you have, you can use in front of you, like your notes, things like that. Okay, the 5, 6 seconds. All right, so select the correct statement about the energy diagrams. So let's look at them. A, the reaction is exothermic. what would an exothermic reaction look like? You would start off high energy and you would end up low energy, right? So it would give off energy. That's what exothermic means. Energy is leaving the system. So this would be exothermic. So is either A or B exothermic? No. So A is wrong and C is wrong because they're both endothermic. You had to put energy in to go from a low energy to a high energy. So they are both endothermic. All right, B, reaction A is slower. What do we think? Yes. So I want you to picture me on a bicycle. All right, this is me on the bicycle. Which one is going to take me longer to climb the hill? Which one am I going to go slower on? A, why? You're absolutely right. It's a higher hill. I have to expend more energy to get to the top of that hill. So in A, it's going to take me maybe 20 minutes to get to the top of that hill. In B, maybe it only takes me 10 minutes, right? Because I don't have to pedal so hard. So reaction A is slower, that is true. So D cannot be true, right? And then E cannot be true. So if you kind of picture these energy diagrams as Dr. B on a bicycle, you can answer most of them. You can answer most of them. I don't know if you want to picture me on a bicycle, but all right, let's see. Oh, wait, I had to do the wrong thing. All right, so good, B. All right. Okay, get your calculators out. Get your calculators out. All right. We have a food label, and this lists the following: 22 grams of carbohydrates, 7 grams of fat, and 5 grams of protein. How many calories are present from carbohydrates? Be careful. How many calories are present from carbohydrates? Give you a minute and a half. Twenty seconds. Okay. All right, so what did we say? Ooh, good. All right, so B is the correct answer choice. How did you get to B? You should have just looked at our carbohydrates, right? It just asked you for carbohydrates. So there were 22 grams of carbohydrates. So all you have to do is convert grams of carbs into calories. And we know that there are 4 calories per gram of carb. Okay? Are you okay on that one? It won't be that easy on the exam. But it was a good refresher, right? All right. Okay. Now, I want you to identify which of the following is true about activation energy. Which of the following is true about activation energy? How many do you have today? I thought it was like 48. Oh, they're above 48. 10 seconds. All right, we're up to 51. That's good. Okay, so activation energy. Let's look at each one. Is high in the reactions that progress slowly. Is that true? I have two reactions. And I'm going to show you two different things. Okay. So tell me about the activation energy in A versus B. A versus B. What do we think? What is activation energy? Anybody? Correct. The amount of energy you need to put in to make the product. So you have to figure out where you started, and then you have to get to your maximal energy point. So here's our activation energy for our first reaction. Now here's where I'm going to start, and this is the maximal amount of energy I have to put in. So tell me about the activation energy for A compared to B. Energy of A is small, right, compared to B. Does that make sense? Okay, so let's evaluate A again. It is high in reactions that progress slowly. What do we know about reaction A? Is that going to go fast or slow? Fast. You're at the top of the hill. It's going to go fast. How about B? Slow. Okay, so evaluate A. It is high in reactions that progress slowly. True or false? True. Okay, B. Activation energy is affected by the presence of a catalyst. That one is true. That one is true. How do we know that? Well, if I had a catalyst in A, my curve would look basically like this. I would start at the same place, I would stop at the same place, but my hill would be a little bit smaller, right? So like a catalyst can stomp down the hill before you have to get going, right? Same thing for here, with a catalyst, your activation energy would be low. Okay, so that's true. The difference in energy between reactants and the highest point on the energy diagram. Is that activation energy? Yeah, y'all told me that earlier. Yes. D, the amount of energy that must be attained by reactants for a chemical reaction to occur. Yes. So guess what? All of the above, all of the above. Okay, so make sure you read all those answer choices. Now, what's a trick when you're doing this? If you're reading something like this, and you have more than one answer choice that ends up being correct, and I don't give you, I know I do it. I do it with the 1 and 2, I do that, I do. But I don't always do that. So if you only have one answer choice, that's all of the above, and then each of the others is individual. If more than one is correct, they all have to be correct. So that's kind of a test taking tip. All right, so I think that's all that I wanted to do for today on Clicker. Yes, but I'm gonna have some more next time. All right, so pull out your in-class problems. No, I'm not gonna say the changes. I don't want chapter, yes, I do want chapter 5. Okay. What page were we on? Ooh, I picked well. I think this is where we left off, right? We had just finished section 5.2, and we were starting 5.3, but I said instead of starting 5.3, we're gonna close it down for the day. All right, full screen. Oh, I'm so happy to be able to write on the screen again. This is so nice. Okay, so characterize the following reactions as synthesis, decomposition, or exchange. I'm going to give you a hint, and I'm going to give you this suggestion kind of now through almost the end of the year, into the semester. When you're reading a problem, if you can write yourself like a couple of notes that are going to help you to solve it, because a lot of times you're going to see lots of chemical equations below, you're going to see lots of structures, right? It's going to be a lot going on. So if you know what you're looking for before you start the problem, you're less likely to get yourself confused. So if I'm looking for a synthesis reaction, what's an example of a synthesis reaction using letters? Like if I did A plus B, how would I predict the product of my synthesis reaction? It would be AB. I'm creating something new. How about decomposition? So we just split AB apart. We decomposed it. How about exchange? So that was, well, so this was decomposition. Oh, this was synthesis. So now, exchange. There are two different ways that you could do exchange. So I'm going to give you the start. What am I looking for in my product? AC plus B. So B and C switched. Okay, what if I did this? AB plus CD. Now be careful with this one. AD, so A and D plus what? Not BC, CB. Now, that might sound picky, but I'm going to explain it. Let me explain it, okay? What if I had NaCl plus KF? I can put Na and F together, and I can put Cl and K together. Can I put Cl and F together? Not unless I'm going to make a covalent compound, right? So what I want is NaF plus KCl. Okay? So be careful that if you're starting with both ionic, that you end up with both ionic in an exchange. Okay? All right. So these are easy. You're just classifying, but I think in the homework I had you predicting products. Okay. So A. What does A look like? It looks like synthesis. Here's my A, here's my B, here's my AB. So this is synthesis. Okay. How about B? B is a special case. You could give it two classifications. Not decomposition, it is exchange, but there's something else that's not in this list that you could also call it. I have a hydrocarbon and I'm slamming oxygen into it.
Oxidation.
Almost. Combustion. Combustion. Anytime that you have a combustion reaction, it's a hydrocarbon plus oxygen gas, and it yields what? I guess I'll go down that way. And it yields CO2, whoa. Maybe. CO2 plus H2O. Okay, that's combustion. So combustion is a type of exchange. Okay. All right, the last one. What's happening? Look at my SO4 and my OH. What's happening? The exchange. Now I have AlOH and KSO4, right? So I've just exchanged them. So that's exchange. So you could call this a double exchange, right? This is a single exchange. This is a double exchange. And some of y'all have learned that a displacement, a single displacement, a double displacement, same thing. I don't know what you've had in high school. Some books call it one thing, some books call it something else. Just need to all get on board on the same thing, right? All right, so determine if our reactions are reversible or irreversible. So let's use my tip. What could I write above reversible that would be a good reminder of what I'm looking for? The double-headed arrow symbol. That tells me that the direction of the reaction could be either way, right? We could go forward or we could go reverse. So what's an irreversible reaction then? Just our old standard yield sign, okay? So in A, reversible or irreversible? Reversible. In B, irreversible. Now, let me ask you something. Even if you didn't, even if this were blank, even if this were hidden from you, right? Could you tell me if this was reversible or irreversible? What kind of a reaction did we say that was? Combustion. What happens in a combustion reaction? Kaboom, right? What are you producing? Just gases. Are you going to get those gases back? No, you just said goodbye to them, right? That is irreversible. So combustion is going to be irreversible. That's kind of a good little tip. Okay, and in C, reversible or irreversible? Irreversible. Good. Y'all got this. Okay. All right, now I'm going to review real quick on 5.25 before we do 5.26. So as a reminder, when you are balancing reactions that are combustion reactions, you can spend a really long time on them, or you can balance them in this particular order. Go carbons, hydrogens, oxygens. CHO. Carbons, hydrogens, oxygens. If you do it in that order, you're going to have less trouble, I promise. And then a lot of times what you also have to do is at one point double everything. So you could do it in the beginning, you could do it at the end. Doesn't matter to me. All right. So when we have our reaction, I'm going to write it again down here. So it's a little bit bigger for me. Okay, what are we going to produce? It's combustion, the complete combustion. We're going to make CO2 and we're going to make H2O. Okay, what order do I balance my equation in? CHO. Hello. CHO. Cho. Okay, so carbons first. Tell me how many carbons on the reactants. So my carbons is 4. And how many on this side? Okay, so what am I going to do? I want to multiply by 4 to get 4, so I need a coefficient of 4. All right, now what? Hydrogens. How many hydrogens in reactants? 10 hydrogens over here. We only have 2. So what do we need to multiply by? So we put that 5 up there. Okay, now we're worried about oxygens. Tell me about oxygens. I have 2, and then how many oxygens on this side? I have 4 times 2 is what? 4 times 2 is 8. And then I also have 5 here, right? So what am I going to get? 13. Can I multiply 2 by anything to get 13? It is never going to happen. So I'm going to take everything and I'm going to multiply everything by 2. Okay? So if I put a 2 here, so that was a 1. So 1 times 2 is 2. Right? Okay. So 2 times 4 is 8. Okay. 2 times 10 is 20. Okay. I'm going to leave my oxygen. I'm going to wait on my oxygen. My carbon, instead of being 4, I'm going to do 4 times 2 is 8. So I'm going to get 8. Okay. My hydrogen, 5 times 2 is 10. 10 times 2 is 20. Okay, so I got my carbons, I got my hydrogens. How about my oxygen? Let's count it on the product side because I have way more of that. 8 times 2, so I'm just going to cross this out. 8 times 2 is 16. 10 times 1 is 10, so that is 26. Can I multiply 2 by something to get 26? Yes, what? 13. So it should be 2C4H10, 13O2 yields 8CO2 plus 10 H2O. Yeah? There's some more practice ones like this in the end of the chapter, if you want to practice a few more. Okay. All right. So now we want to talk about the differences between general chemical equations and organic chemical equations. So in above, we talked about organic. Okay. So above in 5.27, we talked about similarities between chemical equations in organic and chemical equations in biochemistry. What's the number one thing that is different between a chemical reaction that we've been doing all semester long versus our new organic and biochemistry reactions? What do we show in those organic and biochemical reactions? What? Yes, we show bonds. Bonds show us structure. It's exactly right. So it shows us how the things are configured, right? Up until now, we said like C4H10, right? But now you know that you can have different molecules that still have the same number of carbons, same number of hydrogens, but we name them differently because they're structured differently, right? We learned that. So a lot of times in biochemistry, organic chemistry, you not only have to know what atoms are there, but you have to know how they're arranged. So that structure is super duper important. So in our general chemical equations, how did we list our reactants and products? Do we list their structure? Do we show their structure? No, what do we give instead? What do I call this? A molecular formula. Okay, and how about organic? Are reactants and products listed as structures? Super important. Right, and why is that? Because we want to see changes in structure and we want to see changes in our functional groups. Now they're all chemical equations, so they all fall under the conservation of mass, right? Conservation of energy and mass. So you can balance all chemical equations, every last one of them, you can balance it. But if you haven't noticed by now, we've drawn lots of equations that we haven't balanced, right? So yes, they all follow the same laws, but we don't care quite so much in organic molecules about balancing. So we are more worried about structure than balancing the equation. Whereas in general, we just balance it, right? We're just balancing atoms. That's all we're doing. And Caroline, I just saw your question. I'm sorry. Ask me again at the very end and I'll go back and answer. I'm sorry. I didn't see the comment. Okay. Are we all right on that? Now we're doing a new kind of reaction, oxidation and reduction. So what's my little phrase that I want to remember when I see oxidation and reduction? Oil rig. Look, perfect for Louisiana, right? If you could spell. Oil rig. Now, the trick is to tell me, what does oil rig mean? O stands for oxidation. So oxidation is loss or less what? Electrons. So what does rig stand for? Reduction is gain of electrons. So that tells you about half of the equations we're going to cover. But you can't always see electron loss very easily. So sometimes it's easier to watch out for changes in numbers of hydrogens or changes in numbers of oxygen molecules. So I'm telling you, for the rest of these problems, you need to have this little table right next to you. Okay, you're going to use it a ton. So use this little, it's like a little cheat sheet, right? Okay, so are the substances shown in italics undergoing oxidation or reduction? So in A, we have silver ions. What's my symbol for silver ions? I gave it to you. I would not have given that to you. Well, actually I would, because that's a transition metal. So I would give you that one. So it should be Ag plus. Now I could give you something that's not a transition metal, that is a main group element, like sodium. If I said the sodium ion, what would you write for me? Sodium ion, what would I write? Na plus, right? So you need to look in the periodic table and be able to know your charges of your main group elements. So that's kind of a reminder, but we're not doing sodium right now. Okay, so we have silver ions that are electroplated as silver atoms on flatware. When we say atoms, what does that tell us? Ion means charged. What does atom mean? not charged or neutral. Okay. So we're going from Ag plus ions to Ag. And a lot of times we denote that as just an S for solid, right? It's not an ion, it's a solid, so it has no charge. So what charge was my silver to start with? A +1. What is it in the product? 0. So how do I go from something that is a +1 charge to having no charge? I need to gain 1 electron, right? Because if I have a +1 charge and then I add a negatively charged particle, what am I going to get? 0. So if I gain an electron, what must this be? Remember, oil, rig, reduction is gain. So it will be R. Okay. B. D-glucose reacts with hydrogen to form the sugar alcohol D-sorbitol. Do I expect you to draw that structure? Nope, nope, nope. So all you have to do is write, I'm going to say glucose, let me change color here. Glucose I'm going to call A, and D-sorbitol I'm going to call B, right? If I have something and I react it with hydrogen to form B, can you use your little cheat sheet, which my cheat sheet is on a previous page. What am I doing with my hydrogens? Is this a gain of hydrogen or a loss of hydrogen? This is a gain of hydrogen. So go back to your little cheat sheet. So what is a gain of hydrogen? Reduction. Now you know why I said to have that right there. This is a reduction. Right? Okay. Now C. The biomolecule FADH2 loses hydrogen and becomes FAD. So then you can put hydrogen as a product, right? So what's happening with this? It actually says it. This is a loss of hydrogen. So what's a loss of hydrogen? Oxidation. Okay. All right. And you know, we all love to give you more information than you need in a problem. And this is a case in point, right? So although we mine most sodium chloride, it can be synthesized by the reaction shown. Identify the reactant oxidized and the reactant reduced. So let's start with sodium. What's happening with sodium? What's my charge as a reactant? I guess I can kind of move that over. So my sodium. What's happening over here? What charge is it? If it's a solid, there's your red flag. It is 0. What is it going to over here? Now we're going to sodium chloride. Well, sodium chloride together has a charge of 0, but I'm not asking you about sodium chloride. I'm asking you about sodium, just sodium. So if I have a molecular formula, right, and those ones are understood, I can do the reverse crisscross, and I know that has to be -1, and I know that has to be +1. And sometimes this equation is reduced, and so you have to go double check in the periodic table, but you know chlorine's a halogen, so it has to be in group 17 or 7A, so it's going to be a charge of -1, so you know that's right. Okay, so we're going to a charge of +1. So what's happening? Gain or lose an electron? You're going to lose an electron, right? You're going to lose an electron. So are we oxidation or are we reduction? Oxidation is loss. Okay, chlorine. What are we starting out at? 0. What are we going to? A -1, right? How do we go from a 0 to a -1? We're going to gain an electron, and that is reduction. Okay, I'm going to tell you that you already knew this. You did this problem, but you already knew the answer. Every last one of you in here knew the answer. You want to know why? I tell you to write the chemical formula for sodium chloride. What do? You say sodium's a +1, chlorine's a -1. So what does that mean when sodium's a +1? It lost an electron. It lost an electron. What happened to chlorine to become a -1? It gained an electron. We learned about this in like chapter 2, right? You already know this. This is just putting new words to something you already know. Okay, so don't get intimidated by it. It's something you already know. We're just giving it a new name. Okay, how do we know that chlorine is no charge? That's a great question. So all of our diatomic molecules, like Cl2, H2, Br2, anything that is two of the same thing and they're non-metals, they're going to have a charge of 0. Like just like the solid metals have a charge of 0, the diatomic non-metals also have a charge of 0. Okay, good question. All right. Questions on this so far? So far, so good? All right, now we're going to have to look for not only our electron transfer, but we're going to have to look for oxygen and hydrogen changes. All right, so 5.34. Ketone bodies are molecules formed in the liver during periods when carbohydrate intake is restricted. Acetoacetate and beta-hydroxybutyrate can be converted into energy in the absence of glucose. The two molecules are interconverted through the redox reaction shown. What does redox mean? Oxidation reduction, right? It's the same thing, we just shortened it. Identify the reactant oxidized and the reactant reduced. Okay. How many reactants do you have in this equation? Because I know this looks a little bit different than a normal chemical equation. So where are my reactants? Here's 1, beta-hydroxybutyrate. That's 1. Where's my other reactant? NAD+. So this is a reactant. This is a reactant. Where are my products? Here's a product. Here's a product. Does that make sense? A lot of times the smaller molecules that participate in biochemical reactions, we don't write them in the standard format. We write them above the arrow because we're not too worried about them. What we're really worried about is the structure of this product. And so it just kind of gets like sidelined. But they're still reactants and they're still products. Okay? All right. So let's do our smaller molecule first. Let's do our NAD. So we're starting with NAD+, and what do we go to? NAD what? NADH. What happened? We gained a hydrogen. What is a gain of hydrogens? Gain of hydrogen tells you it is reduction. How did I know that? Go back to that little table, right? Go back to that little table. That little table you need to have out next to you. Okay, now I'm not going to redraw everything. So how do I look at beta hydroxybutyrate versus acetoacetate? What am I going to look for? Oxygens and hydrogens. So let's look at oxygens first. How many oxygens are in beta hydroxybutyrate? How many? 3. How many in acetoacetate? So do we have a change in oxygens? No. Okay, I'm going to show you 2 different ways to look at the hydrogens. All right, let's count them all. I have 1, 3, 6, 7. So I have 7 hydrogens on this side, and then I have 3, 5 hydrogens here. So tell me what happened. We lost 2 hydrogens. A loss of 2 hydrogens is oxidation. Now, sometimes the molecules are really big, right? And sometimes you want to be able to kind of cut through this a little bit quicker. So what I can do is I can compare the 2 and I can say, all right, this CH3, I can cross out because it's the same CH3 on that side. Right? So anything that's the same from one side to the other, you can just kind of scratch it out. CH2 is the same, CH2 is the same. Okay, now I have 2 hydrogens versus no hydrogens. It's still a loss of 2 hydrogens and it's still oxidation. Either way works. Right? As I was saying, I think it was last class, more than one way to skin a cat. I say that like way too often. I really love cats. I've had cats all my life. I love cats, but I always say that. Terrible. Okay. All right, so we good on oxidation reduction? It's nothing you hadn't seen before. You know how to count hydrogens. You know how to count oxygens. All you have to remember is that little table. I'm telling you, just that little table. Okay. So what type of chemical reaction is condensation? Synthesis, decomposition, or exchange? Before you answer, what do you think of when you think of condensation? I think I have my nice glass of ice water and I put it on the counter, and what happens to my glass of water? It starts to sweat, or you start to get water condensing on the outside of the cup. So condensation is adding water, okay? All right, so how does that happen? What's going to happen in this kind of an equation? A condensation reaction. I'm going to have one molecule that has a hydroxyl group on it. I have another molecule that has a hydroxyl group on it. What happens when I add water to this? And usually they don't put the plus sign. Usually they'll just put it over the arrow, right? But it's the same thing. What happens? What's another way to write water? HOH, right? So what happens? What happens in this kind of a reaction? Oh no, I'm not. I want to do that. I want to do that. Okay. Sorry. So what happens? What happens in a condensation reaction? You're going to create water. How are you going to create water? So we want a hydrogen and we want an oxygen and another hydrogen, right? So that's going to give us our HOH. So what am I left with? I'm left with an R group, an oxygen, an R group, and a bond. So what's going to happen is this oxygen is going to come over here and bind to this R group, right? So that's how I'm going to end up here. And then this water is going to end up right there. So that's how I made water. I just took a hydrogen from one of the groups and a hydroxyl group from another group, also called an alcohol, however you want to think about it, right? So what kind of a reaction do we have? You're creating something new, so you have synthesis, right? You're creating water. You do have synthesis. But as long as you know how to do the reactions, that's what I'm really worried about. All right, so let's try one. Let's try hydrolysis. What's the difference between hydrolysis and condensation? Because I did hydrolysis on the video and we just did condensation. What's the difference between hydrolysis and condensation? Be careful with this. Look at the pictures I drew. What's the difference between hydrolysis and condensation? They're reverse of each other, right? So in hydrolysis, we're going to break up water in order to make our molecules, right? In condensation, we're going to make water. So you're either making water or breaking water. So which one are we doing in, if I could scroll, there we go. Oh, I gotta go to the next page, sorry y'all. No? It was down at the bottom, okay. So from the hydrolysis reaction shown. So what are we doing in hydrolysis? Hydrolysis is break water, okay? How am I going to break water? Can I break it equally down the middle? Can I give half of an oxygen to anything? I can't do that. So I have to break it such that I'm going to get a hydrogen and I'm going to get a hydroxyl. So now, where's that going to go on our molecule? Remember, this was a kind of our overall reaction. Plus water yields, what are we going to yield? ROH plus, same thing, right? So what am I looking for in this big molecule? An oxygen with two groups attached. An oxygen with two groups attached. Do y'all see that? The only other oxygen in this molecule is the carbonyl oxygen. What happens if I broke the bond for the carbonyl oxygen? If I broke it right here. Would I end up with something that looks like this and looks like this? No, I would have like a free oxygen. That's not going to happen, right? Okay, so I need to break the bond either here or here. It doesn't matter which one you do. It doesn't matter because it's going to work out. Okay, I'm going to leave it like this because the bond's here, so it's kind of easier to see. So what's going to happen? Redraw everything that's over here, and then you're going to add the hydrogen to the one with oxygen already there, and then you're going to add the hydroxyl to the part that doesn't have the oxygen, so that each one ends up with an oxygen. You got to be fair. So H3CO, now I'm going to add my hydrogen from water. There's my hydrogen from water. My other product, right? I want to put my hydroxyl from water, and then I'm going to put the rest of my molecule. So you see where the parts of water went? Those are the ones that are in blue. And that served to break apart our molecule. Okay? All right. All right. Now, Now we're gonna have addition reactions to alkenes. What's an alkene? Let me refresh my memory. Alkane, alkene. Carbon-carbon double bond. So we're gonna add things to an alkene. You can have a hydrogenation reaction. What's a hydrogenation reaction? We're gonna add what? Hydrogenation means add hydrogens. Add hydrogens, okay? So it should have been shifted over this way. So I'm just gonna write my products over here. Sorry about that. All right, so whenever you add hydrogens, how many carbons are participating in the alkene double bond? 2. How many hydrogens do we have? We got 2. So we got to be fair, right? We're going to give each carbon that participates in the double bond a new hydrogen. But what's my problem? I can't just stick extra hydrogens on there and call it good. What's my problem? I got to get rid of that double bond because right now I have 2, 4, 6, 8, 10 electrons around my carbon. Is that going to work? Absolutely not. So in order to do that, I need to basically get rid of that bond right there. So I'm going to draw my new product. Right up here, I have CH2, CH2, CH3. Then I have hydrogen and hydrogen. And now I have the original hydrogen, and I guess I could put those in blue, the new ones, so that you could see. There's my new hydrogen. Here's my new hydrogen. And then I have, now don't get confused at this. Do you see this? Do not get confused with this. This is the same thing as if I had written carbon and then said that's a CH2 and then CH2, CH3. All they're doing is showing you that the carbon here is bonded to the carbon and not to the hydrogen. But it's the same thing. But like, I don't know why they didn't do it before and now they're doing it now. I don't know, because they're inconsistent. What can I say? All right, so it doesn't matter which way you write it. Well, I guess it does matter for the homework. It actually does matter for the homework. Okay, so we'll do it the way they like it, because it will matter. See, and then I can't squeeze it in H3. I'm running out of room. But this whole thing right here is this, because it has to be exactly the same. The only thing that's changing is you're adding hydrogens and then removing that double bond. So now when you get to the skeletal structures, gosh, I love doing the skeletal structures. They are so nice and easy. All you have to remember for your skeletal structures is to count your carbons. If you count your carbons, you're going to get it right every time, okay? So let's look at B. In B, here's our double bond right here. So I'm worried about this carbon and I'm worried about this carbon. I'm going to give each of those a hydrogen. But what do I know about the structure when I draw skeletal structures in general? We don't show hydrogens. So all I really have to show is the loss of my double bond. But be careful because double bonds are drawn this way, whereas when you have single bonds, they're always drawn right at angles. So don't draw it as a straight line anymore, draw it as an angle. This is why counting your carbons is important. So what I like to do before I do the problem is to count my carbons. 1, 2, 4, 5, 6, 7, 8. And it really doesn't matter if you start from either end because we're not naming it. It doesn't really matter. You just need to have 8 carbons and then 1 methyl group coming off of carbon 5. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5. We're going to put our methyl group. How nice is that, right? Okay, now, C. Where are we going to put our hydrogens? We're just going to add them on either side of the double bond. But what kind of structure is this again? It's skeletal. So we just got to get rid of the double bond, right? We don't have to show our hydrogens. So when we draw it, kind of like a house that kind of comes in. I said I was drawing with the mouse last class, and my houses looked so sad and dumpy. It was really, really sad. But there's your structure. It's just missing the double bond, right? So gotta love those. Those are nice. All right, now we're going to do the same thing. We're going to write the product, but this time, instead of adding H2, what are we going to do? We're going to add water. So we're going to use the same equations, but this time, instead of adding hydrogens, we're adding water. So hydration, right? If you are dehydrated, I'm so thirsty, how are you going to hydrate? What are you going to do? You're going to drink, or you're going to add water. So in this case, we're going to add water, we're going to add water, and we're going to add water, right? So the reactants are the same, but this time we're adding water instead of H2. So how is this going to be different? So now you need to break up your water, but you can't break up your water equally, right? So when you do that, you're going to end up with HOH, right? And you're going to break it down the middle so that one side is going to get hydrogen and the other side is going to get the hydroxyl. How do you know which side gets what? Hydrogen, put this, hydrogen likes hydrogen. Okay, so what that means is if we look at our two carbons that are associated with the double bonds, and you look at what is attached to those carbons, this one has one group with carbons in it, this has one group with hydrogens. It's the same thing with this one. So this one, it doesn't matter which side gets the hydroxyl and which side gets the hydrogen. But it will if, for example, we started out with this. What if we started out with this, where we had two hydrogens on one side and then a methyl group, peanut butter, butyl group, and a hydrogen. The hydrogen would go with the hydrogens, but it doesn't matter for this one because they're both the same, okay? So if we look at this, what are we going to do? We're going to add hydrogen to one carbon, hydroxyl to the other carbon, and get rid of a double bond. So what should my product be? Same thing, except now we have four things around each carbon. I guess I should have done them in a different color, but this will be an OH, and this will be that weird way to write. Make sense? So you just give part to one and part to the other. Okay, how about B? How about B? Let's write what B really is. So if I just focus on these two carbons, the carbon double bonded to a carbon, then we have, right, two carbons. Then we have, coming off of this one, 1, 2, 3, 4, 1, 2, 4, and then we have one carbon coming off of here. So what else is attached to this? Are all the carbons happy? Do they all have an octet? We have hydrogens. We have hydrogens. Where do we have a hydrogen? On the first carbon or the second? Look at my first carbon. My first carbon has a bond here, so that's 2, a bond here, 4, 6, 8. So that one's happy. How about my second carbon? 1 bond here, that's 2, 4, 6. Uh-oh. What is it missing? A hydrogen. There's really a hydrogen there. We just don't write it. Yeah? So now, what am I going to do when I split my water up? Which carbon is going to get hydrogen? Which carbon is going to get hydroxyl? Carbon, okay, let me put it this way. It's hard for you to answer these questions, right? Which carbon is going to get the hydroxyl? Carbon 1 or carbon 2? The hydroxyl is the OH. Carbon 1 should get the hydroxyl. I should do the other way around, right? OH. This one should get the hydrogen. Why? Hydrogen likes hydrogen. So you're going to put hydrogen with the other hydrogen, and then you're going to get rid of the double bond. But this is kind of a crazy structure, right? And we don't really write our hydrogens. So I can kind of erase my hydrogens, right? Because I just don't show them. So then how could I rewrite this formula? What I'm trying to do is add a hydroxyl here and add a hydrogen here. So how would I redraw my structure? What was my tip to you? Count your carbons. 1, 2, 3, 4. Now carbon 5 is going to get an OH and it's going to get a methyl group. 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then carbon 5, 1, 2, 3, 4, 5 is going to get a methyl and it's going to get a hydroxyl. Y'all okay on that? Just count those carbons. Count those carbons. Okay, and C. Which one's going to get the hydroxyl? Which one is going to get the hydrogen? Does it matter? Doesn't matter. Doesn't matter. Because going this way or going this way, it's the same molecule. So it doesn't matter. So when you draw it, either one of the carbons attached to a double bond, that's right. So when you draw it, how are you going to draw it? How's it going to be different? A little house. What do I need to add to my house? Right, because one of these is going to get a hydroxyl and one of these is going to get a hydrogen. So what do? Just draw a hydroxyl on actually any point, because I could rotate this in 3 dimensions and it's the same molecule. So technically you could put it on any corner and it would work, because you would name it the same thing. Think about, would it be the right structure? Does it matter if my product would end up being named the same thing? Then it doesn't matter. Okay. All right. So that is the end of chapter 5. What do y'all have due tomorrow at 9 p.m.? Chapter 5 homework. There are a very, 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 very few number of people who have submitted or started working on Chapter 5 homework. Do not wait until 8 p.m. Please do not wait till 8 p.m. to start working on it. Because there's some drawing in there, and I know that kind of takes some people some time. So make sure you have enough time to get it done. All right. All right, and let me know if y'all have any questions, but that's it. And Caroline has a question. How do you know? Okay, 5.24. Hold on. Let me go up. 5.24. Thank you, Caroline, for asking me again. Okay, 5.24C. You would have to know, for this one, you would have to see the symbol. You would have to know that 5.24C. In 5.24B, you wouldn't need the symbol because you know that is combustion. So combustion is irreversible. But this one, C, you would need to have the arrow. Does that answer your question, Caroline? All right. I'm hoping it does. Yes. Okay, great. Awesome. All right. If anybody else has questions on Zoom, please go ahead and type them in. And if I don't see any in a minute, I'm going to go ahead and close it. Y'all have a great rest of your day. I'm turning off the mic. Okay. Got it.
Okay, so is this number going to change whenever you change? Sorry. Is that number going to change whenever you change this?